Okay, welcome everybody to the final lecture of differential geometry series this week. So let me start with a brief summary what we have seen this week, okay, and then I will continue. So let me point out the main concepts what we have seen this week. So let sigma be a surface patch with standard unit normal n. Then the first definition what we or the first concept what we understood in the first lecture, it was the first definition of a second fundamental form, so which was given by L du square plus 2m du dv plus n dv square. So this was called second fundamental form. So where L was sigma uu dot n, m was sigma uv dot n, and n was sigma vv dot n. Okay. So as we have seen that this was actually kind of a measure of how the surface was curving at some point, or in other words, it was measuring the curvature of the surface. Okay. So then we computed explicitly for some examples using these formulas, like directly if we have a surface patch, then if we can compute the unit normal n, then you just take the dot product and then you compute it. So we did that for some examples. So then in the next lecture, what we found out another equivalent definition, as I am repeating this many times, that we approach the same concept from a different ways and somehow arrived at the same concept. So here we defined a Gauss map, which is a map from the surface S to the unit sphere, sending a point P to the normal unit normal at NP. And correspondingly, we defined a Weingarten map, is WPS, is nothing but minus dp, so minus derivative of the Gauss map, which is a map from the tangent plane to the tangent plane. It's a linear map. And then we defined again the second fundamental form as a bilinear form defined by BWPS for a point P in the tangent plane. Sorry, P in the point in the surface, and V and W are points in the tangent plane. So then this was nothing but the inner product given by WPS V with W. And this one should immediately object that why do I call this also second fundamental form, where I have already defined a second fundamental form. But this is coherent because we saw that how this definition is actually equivalent to this definition, because both of them give the same bilinear form. Okay. So then we came in the next lecture, we defined another invariant, which is called normal curvature. So this for this, basically first you consider a unit speed curve gamma on an oriented surface S, then you can take as a working definition as the normal curvature kappa n. This you can think of as the projection of the gamma double dot to the unit normal. So gamma dot 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 n. So, and finally we saw that this definition also actually gives the same bilinear form as this one. So essentially all these three are equivalent. So all three basically contain same amount of information for a given surface. Okay. So once we were happy with the definition of this invariance, then we proceeded with some more geometric details about the surface. So the next thing, what we defined was a Gaussian curvature. So what was that Gaussian curvature, which we denoted by K? This was nothing but determinant of this Weingarten map. And similarly, we also defined a mean curvature, which was denoted by H as half of trace of W. So this again, this makes sense because W is a linear map. So we can get a matrix associated with the linear map, and then we can take the determinant. And similarly, we can take also the trace. Yeah. And then in this chapter, we saw that how to compute it explicitly in terms of the matrices given by the coefficients of second fundamental form and the first fundamental form. And finally, we computed this for many examples, and even we saw a very nice application of Gauss, figuring out how to compute the Gaussian curvature without computing the determinant. So essentially, it was like measuring the area of the Gauss map per unit area. So this also we saw. Then finally, in the last lecture, we saw another interesting notion, which was principal curvatures. So what are the principal curvatures? So this actually, we also saw this, that this W, the Weingarten map, this is actually a self-adjoint linear map, or in other words, this bilinear map, this is a symmetric bilinear map. So in other words, then we would have a basis of eigenvectors of W, and then we would of course have the corresponding eigenvalues and eigenvectors. And principal curvatures are actually the, so principal curvatures are eigenvalues of the self-adjoint W, and correspondingly principal vectors are corresponding eigenvectors. Yeah. And once, so this, let's say this, you say this is kappa 1 and kappa 2, these are the principal curvatures. So immediately you get a nice reinterpretation of the Gaussian curvature in terms of K will be product of kappa 1 times kappa 2. This is not a dot product. Let me be, yeah, so this is kappa 1, kappa 2, and H would be half of kappa 1 plus kappa 2. Yeah? So this is just from the definition, and this we saw actually also how to prove this, that these principal vectors, they can form a basis, and in terms of that basis, the matrix is a diagonal matrix with K1 and K2 of the diagonal entries, and then the Gaussian curvature was the determinant, which came like this. Okay, so this is essentially what we have seen. And then finally, I ended yesterday's lecture with a proposition, which essentially gives us the theme for the next part. Like, as I was trying to motivate you, that once you have defined so many invariants, it's a very natural thing to do in abstract mathematics to classify the objects once you have defined some invariants of the objects. So the first proposition, what we have seen yesterday, so we saw how to classify in terms of principal curvatures. And here what we proved, that let S be a connected surface of which every point is umbilish. So what was the definition of umbilish? So could anybody help me with the definition of umbilish? What was the definition?
When K1 equal to K2.
Yes.
C equal to K2.
Yeah. Yeah. So essentially the eigenvalues are the same. So K1 is equal to K2. Yeah. So if this is the case, if every point is umbilish point, then essentially S is an open subset of a plane or a sphere. So we actually computed that for a plane and for a sphere, the principal vectors are either 0 or 1 essentially. And what this, I mean, if it's a unit sphere, that it's 1. I mean, otherwise it's with proper radius. But the main content of the proposition is the converse is also true. So these are the only case when this condition can hold, that every point is umbilish point. And let me warn one another thing. I realized yesterday when I was talking in this definition umbilish, sometimes I have missed this I. So maybe I have called this umblish, but in the note I have actually corrected, but maybe, I mean, don't be confused, okay? So this is called umbilish, not umblish. Yeah, but you get the point. I mean, so this was the first example of the classification of surfaces. And now I will continue with another way, or like, let's say, another avenue, how to classify surface, or how to find out how the principal curvatures at a point P somehow provide information about the shape of the S. So this is for example already an example, right? That if every point is umbilish, then it is compulsorily be a part of a plane or a sphere. But this is not necessarily true, right? I mean, this is a very strong condition to assume. So we can't just assume this condition. So let's try to be a little bit more general. So let me build the background first. So for simplicity, we are taking P in S a surface, arbitrary surface, and we can take P to be origin. And we can also consider TPS, the tangent plane, that is to be then XY plane. So if we consider P to be origin, then TPS, if you just apply some, let's say, shape preserving isometry, then you can consider this TPS to be a XY plane. So this, without loss of generality, you can assume. So let me continue with the assumptions. Further assume the tangent vectors T1 1 0 0 and T2 is 0 1 0. So they are actually principal vectors corresponding to principal curvatures kappa 1 and kappa. Okay, so this also you can assume, if let's say if you don't get this vector, then you can take a rotation around z axis and somehow you can convince yourself that this simplification is without loss of generality. So this is okay. And in a similar way, you can further assume, if needed, by taking a reflecting in the xy plane if necessary, the unit normal of S at the origin at P is N is 0, 0, 1. That's the other side, right? I mean, so here T1, T2, and this is the unit normal. Okay. So now let me consider a surface patch. Consider a surface patch sigma of S with sigma 0, 0 is vector 0. Then for all xy in R, you would have unique existence of S and T such that x, y, 0, this is nothing but S sigma u plus T sigma T, right? Because that's just by definition, sigma u and sigma T are linearly independent, and they just kind of a basis for this part and xy, and then you can write this. So once you have this, this will be again similar to what we started in our first lecture actually. So we'll take the Taylor's theorem again for two variables. So Taylor's theorem. So what does it give? Around 0, 0. Okay. So we find sigma st is nothing but sigma 0, 0 plus s sigma u plus t sigma t plus half s square sigma u u plus 2st du dv plus t square dv, and plus higher order terms you can just ignore for the time being, because so if you take, let's say, for small s and t, so which means no, let me take, sorry, let's say for you take for small xy, hence you are taking also for small s and t. So then you ignore the higher order terms. So this gives you that sigma st. So here sigma 0, 0 is 0, right? That's what you are assuming. So sigma st is nothing but is actually x, y, z, where z is actually half of this whole part. I mean, so this part you are getting, it's the xy0 part, and z you are getting essentially half of a square sigma u plus 2st du dv plus t square dv. So this is nothing but, now you can think this as half of L a square plus 2ms st plus n t square, right? This is the definition of the second fundamental form. So this is given by the second fundamental form. So this makes sense because here our unit normal is also 0, 0, 1. So this goes through. And now, so what are we trying to say? Essentially, so this sigma st is xyz, and z is essentially approximated by this equation. And that's the surface patch. So essentially, it's kind of a parametrization. So we are trying to find an approximate parametrization. So what I'm saying is, so for if you take now for t equal to s sigma u plus, so this is t sigma v l s square plus 2 m s t plus n t squared. This is nothing but inner product of tt, which is nothing but inner product of wtt. And for you, if you now write t equal to x in terms of the principal vectors x t1 plus t2, then this implies what? wt is, since w is a linear map, wt1 plus yt2 ywt2. So this is nothing but k1 x t1 plus k2 yt2, because wt1 is kappa 1 t1, that's by definition, and wt2 is kappa 2 t2, that's by definition of the principal vector. And this you can actually now think of as a coordinate kappa 1 x kappa 2 y 0. And this finally gives you that l s square plus 2 m s t plus n t square. This is nothing but the inner product of wt and t. So this is kappa 1 x kappa 2 y 0 dot product with x y 0. So it's like k1 x square plus k2 y square. So finally, what I'm saying is, so near P in S, Z is actually approximated by half kappa 1 x square plus kappa 2 y square. So that's my parameterization. That's what I'm saying, right? I mean, so here we have found out that Z is half of the second fundamental form, and the second fundamental form is given by the inner product of the Weingarten map with T, and then we have written W of T in terms of this, and T is essentially this, and then we have just taken the dot product, and this is what you find, that half of kappa 1 x square plus kappa 2 y square. So essentially for a general surface S, for any point P in S, you can find out that the parameterization Z is kind of approximated by the quadric surface given by the equation this one. Okay. So once you have this, why I took this long detour, I mean, once you have this, now there are some canonical choices, right? I mean, here we can now start the classification. So that will be my first case. So case one. So case one is, let me write this down here also so that we will be having this here. So what we have, Z is half of kappa 1 x square plus kappa 2 y square. And let me term this as star. Okay. So what's the first case? So the first case is K1 and K2 both are positive or both are negative. Okay. So in other words, since the Gaussian curvature K is actually product of K1, K2, this is always positive. That's the case I am considering. Okay. So when that is the case, then this equation star, when this condition are satisfied, then this was actually, I don't remember whether it was explained in the previous week, but it's actually a known equation, and this is called, so the star, this equation is actually given by is equation is of it's a surface called paraboloid. Elliptic paraboloid. Yeah. And if this is the case, then P is called an elliptic point. So this actually you can check the book by Presley in the section 5.3. Here you would find very nice pictures of this. So when this is true, then you can get the classification. Then the next case is K1 and K2. They are of opposite sign, and both are non-zero. Both are non-zero. So what does that mean for the Gaussian curvature? So K is essentially less than 0. Okay. So if this is the case, then again you can actually see it's a known equation again. So then this star equation, this is the equation of a surface called hyperbolic parabola. And P is called a hyperbolic point of a surface. Okay. So what did we say till now? If the Gaussian surface is positive, then you call P is elliptic point. If the Gaussian curvature at P is positive, if the Gaussian curvature at P is negative, then you call P is hyperbolic point, or in other words, in terms of K1 and K2 also you can say. So now comes the next two cases, which are in terms of actually Gaussian curvature, you can think of as a single case, but let's divide this out. So case 3, one of kappa 1 and kappa 2, this is 0, but the other is non-zero. So one of the kappa 1 and kappa 2 is 0, but the other one is non-zero. So in that case, the Gaussian curvature is 0. Then the equation star, this is actually an equation of a parabolic cylinder, and P is called a parabolic point of the surface. It's called parabolic point. And finally, the last case, when both K1 and K2 are 0. So in that means K is also 0. So that's exactly what I was saying. K equal to 0 is in this case also, K equal to 0 in this case also. And if this is the case, then star is actually equation of a plane. This also we have seen, right, already. And then P is called a planar point. Yeah. Okay. So these are the four classification in terms of kappa 1 and kappa 2, or in terms of the Gaussian curvature. So one thing is, one immediate thing one should always observe, that this classification is actually independent of surface patch sigma, what we have chosen here. Like here, we have chosen some surface patch sigma. That's why we got finally this parameterization. But you can actually prove that this is independent of the parameterization. Why? Because if you change the parameterization, then the principal curvatures kappa 1 and kappa 2, both are actually either unchanged or they change the sign of the both the principal curvatures. So this is actually also exercise in the book also. So this changes nothing then in our classification. Okay. So this is quite nice. I mean, essentially, this is kind of a classification of points, what it can be in a surface, let's say, I mean, point in a surface in terms of either principal curvatures or Gaussian curvatures. And in a similar way, you can actually also get a very nice proposition. So let's say if S is a compact surface, then there exists a point P in S such that the Gaussian surface K at P is no, let me, so there exists a point P at S at which the Gaussian curvature is positive. Okay. So what I'm saying is, if you take a compact surface, then you can always find a point P in S at which the Gaussian curvature is positive. I mean, let's see here what are the cases of Gaussian curvature positive. So K is positive, and in this case we are terming this as elliptic point. So essentially what I'm saying in this proposition, that if S is a compact surface, you can always find an elliptic point. And if you remember, just today itself, I recalled you another proposition which we also saw last lecture, that if you had a sphere, then for the sphere, you have kappa 1 equal to kappa 2 equal to some radius. And in that case, also the Gaussian curvature was also positive. So sphere is, of course, an example also for an elliptic point. So let me just recall two immediate things, because I don't remember if you recall these things. So maybe if you do remember, then just should not bother. So when is a subset X in R3 called compact? So X in R3 is compact if it is closed and bounded. So for example, sphere is an example, or torus is also an example. And I'm going to use another fact of a compact set. So suppose X is a compact subset of R3, and F is a continuous function from R3 to R, then there exists PQ in X such that FQ is lesser equal to FR is lesser equal to FP for all R in X. So in other words, what I am saying is, so that F actually attains its maximum at the point P and minimum at Q. So this actually just you can prove from the continuity and closed and boundedness property. So this then holds actually. Okay, so this I'm going to use this fact to prove that if S is a compact surface, then you always have a point P at which the Gaussian curvature is positive. So how does one prove this then? So let me just quickly go through the proof. So first, define a continuous map FR3 to R by sending a vector V to the norm square. Now, the previous remark 2, this gives you that there exists a point P in S such that F attains its maximum value. So this actually immediately gives you that S is contained in a closed ball of radius P with origin as center, right? So this is quite immediate, since the for any point P in S, that will be the kind of maximum. So it's contained in a closed ball of radius P. So the idea is actually to show the Gaussian curvature K at this point P is greater than 1 over P square. So in other words, what I'm saying is S is actually at least as curved as the sphere at P. Okay. So how does, I mean, if we can show this, then that is also greater than 0, right? So then we are done. Yeah. So let me go through it quickly, and we are running out of time fast. So I mean, that's the idea, and let's try to be formal now. Let gamma t be any unit speed curve in S passing through P when t equal to 0, and we then have f gamma t has local maximum at t equal to 0, and this gives us d dt of f gamma t is 0, and d square of f of gamma t, this is lesser equal to 0. And this, in other words, if you use the other, this is gamma naught, a gamma 0 and gamma, this is 0. And if you use the unit speed is gamma double dot 0 plus 1, this is lesser equal to 0. So this, let me term this as double star. So essentially what I'm saying is you get P is perpendicular to every point in the plane for the every unit tangent vector, and essentially then P is perpendicular to the whole plane TPS. And now if you choose a surface patch sigma containing P, so this will then give you the unit normal is nothing but plus minus P divided by P. So then you have the normal curvature kappa n, which we have seen again today, the definition gamma double dot 0, and you take dot product with n, and this would imply that this star star would shows that kappa kappa n is actually either minus 1 over mod p or greater or equal to 1. That's just by definition of n, and you just use here. I mean, you use the definition. Now, if you remember yesterday's lecture, there was a very nice geometrical interpretation of the normal curvature in terms of principal curvatures. They were actually the maximum and minimal. It was the corollary to the Euler's theorem. So corollary to Euler's theorem, it said that either kappa is both of the kappa are both lesser equal to minus mod p or greater equal to 1 over mod. And this would then essentially, if both of these are lesser equal to minus 1 over norm p or greater equal to 1 over norm p, this gives you the Gaussian curvature k, which is equal to k1, k2, is actually greater than 1. And then we are done. So that's exactly what we started to do for. So if this is the Gaussian curvature, if it's greater than 1 over norm square, then this is a positive number. And then you are done with the proof. So essentially what we obtained, that what does the proposition says? Yes, so if you have a compact surface, then you always have an existence of an elliptic point. So which means you have a point at which the Gaussian curvature is positive. Okay, let me here remark a very nice corollary. So remark, this you will understand more in the next week. Okay, but still I wanted to state this. So next week, you would see one of the main things, which is called Gauss-Bonnet theorem. So which will tell you, if you integrate over the whole surface of the Gaussian curvature, then this is actually 2 pi times something called Euler characteristic. So where chi is Euler characteristic. So don't bother. I mean, if you don't understand this, just think of today is just a number. Okay, so this is called Euler number of some triangulation. So please do not bother if you don't understand this. But what I want to stress is, if you integrate the whole, or if you take the total curvature of the Gaussian curvature, you get something very nice, which is a very strong theorem. I mean, it's for arbitrary surface, you are getting this number. So if you take S is not homeomorphic to a sphere, then you would see that this chi is actually non-negative, the Euler number. So essentially what you are saying, the whole integral is then non-negative, because 2 pi is, I mean, this chi is then non-negative. So then this is non-negative. So from the previous thing, we have already seen that k is positive for at least in a small open set, because we have seen already existence of a point at which k is positive. Now the immediate thing you should think of, k, if you have a surface such that the Euler number is negative, then you cannot have k positive for every point, because if you have k positive at every point, then the whole integration would be also positive. Then this guy will be also positive, but this is non-negative. So what you are saying is, for a surface of this kind, you immediately get, so this gives you that exists also a point at which k is negative. And by in analysis, actually you also have something called intermediate value theorem. So this gives you actually, what is kappa? Kappa is actually a map in U and V in the parameters. And this is also a continuous map. Now you have a continuous map which is non-zero, I mean, which is negative at some point, which is positive at some point. Then you will also find a small surface patch where kappa will be 0. So what I am saying is, finally, the conclusion is, it's a very nice conclusion. So if you have a surface which is non-homeomorphic to a sphere, then there will be some surface patch where the Gaussian curvature is positive. There will be some surface patch where the Gaussian curvature is negative. There will be also a surface patch where the Gaussian curvature is positive. Okay. Any questions? This was maybe a little bit fast, but yeah. Okay. So if not, then let me continue with the classifications of the next kind. So now let's consider surface of a constant Gaussian curvature K. And we take a special, we consider again a surface of revolution given by sigma uv is fu cos v, fu sin v, gu. And here for this surface, we have already seen the Gaussian curvature K was given by minus f double dot by f. This we have already seen. Let me say this is as start. So this we have seen, actually, this we computed. Now what I want to tell you, just some few more special cases, like, so here if we again take the first case, is K equal to 0 everywhere. So that means what? This star equation gives us that f double prime is 0. And this means you would get fu is au plus b for some constant a and b. But we know that f dot square plus g dot square is 1. This was an assumption on the surface of revolution about this planar curve given by fu gu 0 is unit speed. So this gives you g dot is actually plus minus 1 minus a square. And if you take the sign properly, then gu will be actually 1 minus a square u plus c. And with clever translation along the z-axis, you can also consider c to be 0, and you can consider only the plus sign here. So then this implies the surface patch becomes sigma uv is b cos v, b sin v, 0 plus u a cos v, a sin v, root 1 minus a square. And if you recall this is actually a parametrization of a ruled surface. Okay. It's a special case of a ruled surface. And if you recall, I mean, in the Gaussian curvature chapter, I actually gave an example of a ruled surface, and where we saw that K is always non-negative. So this is one case where K is the specific type of curvature here. So for example, you can immediately, if it's a ruled surface, and it's still quite general, right? So you can immediately get some special cases. So like, for example, if you take A equal to 0, this is a case given by circular cylinder. If A is 1, this is actually nothing but the xy plane. And if 0 less than 1, this is nothing but circular cone. So these are all special cases of the ruled surface given by this parameterization. Okay, so that's the first case. So the second case is K is positive everywhere. And I'm just trying to show you what we obtained somehow in the previous lemma and corollary. it's more general, and here we are considering for a specific surface basically, and we are getting the similar conclusion again. So here I'll not be now more specific. So here I'm assuming that k is positive everywhere. So let's say k is given by 1 by r square, and then the equation triple star, this was the equation here. So this gives me f double prime plus f over r square. This is 0. And you can solve this, and general solution actually is given by fu is a cos u over r plus b. And accordingly, then you can also solve g, which is an integration over a terrible complicated thing, 1 minus a square divided by r square sine square u by r du. But in particular, if you put a equal to r, so then this goes away, this is 1, and this basically simplifies, and then we get actually a sphere, which we knew, right? Sphere is also an example of a surface of revolution, but that's the only example where k is positive everywhere. That's the important thing. And then the final example, which we have not seen yet, the strictly negative Gaussian curvature everywhere. So here we'll consider one particular case. So let's say k equal to -1. And then again, you can find some general solution of the equation star. For this case, fu is actually given by a e power u plus b e power minus u. So, let me write this down again. So fu is given by a e power u plus b e power minus u. Then one can actually get the parameterization as z equal to root over 1 minus x square minus cos h inverse 1 over x. So this is what sometimes people call this as a tractyx. So that's the surface, and it has a nice geometrical shape. So this is like a funnel kind of thing. So something like this. So this is an example of a surface where the Gaussian curvature is actually negative everywhere. Okay, so this completes the classification of the surface of constant k, where we took a particular surface of revolution. I mean, it's a particular example. And for a general surface, for a general compact surface, we have already seen this classification. Like, we have been able to find a point where k is positive, and we also have been able to find a point which is, if it's not a sphere, then we have been able to find a point where the Gaussian curvature is 0 or negative. So in some sense, what I'm saying is we have already shown that all these case 1, case 2, case 3, case 4, all of these cases will definitely occur if S is a compact surface which is not a sphere. So for example, torus, I mean, that's an example. And if you consider a surface of revolution, then you find out all this thing. And then finally, I will conclude. I mean, there is another kind. I mean, this you can continue many times. So consider another classification actually. So it's about, let's say, flat surface. So what is the definition of flat surface? So the Gaussian curvature is 0 everywhere. Okay. So then you have a proposition which I will not prove anymore. It's kind of similar how we have already seen, that let P in S be a point of a flat surface S, and assume P is not embellished. Because if you have to remember, if we have assumed that every point is embellished, then also we have seen the classification, right? That's where, yeah, that's exactly where we have started with. So if every point is embellished, then also it's a part of a plane or sphere. So that's the first classification we take. So now we assume that you have a flat surface, so that means k equal to 0 everywhere, and you assume the P is not embellished. Okay, so then there is a surface patch of S which contains P, containing P that is actually a ruled surface. Okay, so essentially what I'm saying, I mean, let's come back to here. I mean, yeah, for this one, that's what I wanted to show you. So if we consider the surface of revolution, for example, which is a kind of a general example, and here we have already seen this. If k is 0 everywhere, then we have already seen this, that this sigma ub is actually a ruled surface. So that's exactly what I'm saying, that if you have a flat surface and you have a point P which is not embellished, then this is true actually for any surface. I mean, here I'm not talking about surface of revolution, right? So here this was a particular example of a surface of revolution. And here if we assume that k equal to 0 everywhere, we found out that the parameterization is given by the parameterization of the ruled surface. And so in other words, if k equal to 0 everywhere for a surface of revolution, then the surface is given by the ruled surface. And here what I'm saying, it's true even more general. So if you have a flat surface, which means the k equal to 0 everywhere, and assume there exists some point which is not embellished, so that means the principal curvatures are distinct, then there is a patch of S which is actually a ruled surface. Okay, and I mean, how would you prove? It's kind of again how I proved, for example, this one, that if S is a compact surface, then there was a surface patch which is like a sphere. So it's again similarly, I mean, you just have to use the definition of embellish, and then you just show that the equation of the ruled surface, this is actually satisfied for the surface patch, and then you are done. I mean, you just use the. Okay, so in a similar way, essentially you can continue also classification of surface with mean curvature. That also there is a chapter in the book, you can also have a look if you are interested. And yeah, and mostly I guess that covers everything. I mean, what kind of classification you would be able to find. I mean, so let me just end this with the final summary of the classifications. So the first classification, what we did was, if we assume that if for a connected surface, for every point, if it's an embellished point, then it's a part of a plane or a sphere. Okay, that's the first classification. Then what we did, if it is not embellished, then essentially we found out the parameterization is approximated by this one, this equation. And then we divided in 4 cases, or in terms of Gaussian curvature, 3 cases, like capital K positive, strictly negative, and equal to 0. Accordingly, we called it elliptic point, hyperbolic point, parabolic point, and planar point. And then we found out a very nice proposition that if you assume further that if S is a compact surface, then there exists a point P in S at which K is 0. So in other words, there always exists an elliptic point. But then I told you that if you believe me for the time being about some big theorem, which you will see next week, then you can prove that not only K is positive for at least a point, you can also find a point where K is negative. You can also find some point where K is positive for a surface which is not sphere. That's very important, because if S is a sphere, then you know the Gaussian curvature is always 1 or some radius. I mean, it's always positive. This we have already seen. And then we started with some more assumptions, like if you have a constant Gaussian curvature, and we took some particular case, surface of revolution, and then again we classified for K equal to 0 everywhere. Then we found out this is the rule surface. K greater than 0 everywhere, then we found that we get a sphere, and K less than 0, then we found out some fancy surface which is called tractics. And what we can actually show that this case 1, this is not particular to the surface of revolution. This is actually true, even more general, that if you consider a flat surface, which means the Gaussian curvature is 0 everywhere, and if you assume that the point is not embellished, then it's part of a surface patch which is the ruled surface. And that finishes kind of the nice classifications of this. Okay, I'll stop here. Please ask any questions, any comments, anything.